Okay, let's continue the fabrication steps. And now we, after the lithography and then the um, lithography, and then this is the step that you may need, that this is called the post-exposure bake, and then develop. Or this particular step necessary to for some negative photoresist like SU8. So after develop done, after the expose of the UV light done, and then you need a certain the baking process, okay, and then for this step, basically to help the developing, and then the so after the post exposure bake, like for certain for negative photoresist, there is some recommended step, so you can follow the certain the baking step, like you put expose the vapor on convection oven like a certain temperature, like 100 degrees C for like a 10 or 15 seconds. So in after that, then you can wait until the substrate is completely cooled down before it's developed, and then you continue for the develop, and then rinse the material, right? So those things are the necessary step, and then dry with the nitrogen gas. Okay, the post bake for the negative photoresist after the post exposure baking, you also need a hard bake, like post bake, or for the positive photoresist after you expose, and then this is usually the next step for the hard baking. So in this step, then after the hard baking, actually the vapor that having that particular pattern is ready to be used for like some etchings and then some other process. Okay, so in this post bake process, basically you want to make sure your pattern, the PR, is stable, right, to withstand the you know the like etching process and any other process after this. Okay, so to do that, so basically this is you stabilize and then harden the developed photoresist prior to the processing steps, where the resistor will be used as a masking material, right? Um, so post-bake also remove any remaining traces of solvent or developer. Um, Also, because after the hard baking, the structure will be the pattern structure, pattern the PR structure will be used for like a coating or etching, right, to protect the substrate. Um, you should avoid any residue stress. Okay, so to do that, actually slow cooling is important for the thick photoresist after hard baking. So you should let the vapor cool down slowly to the room temperature, and then you can move on for the next process. Um, this particularly this form force baking is necessary for acid etching process like a BOE. Um, so the form the post baking is important before BOE. Um, okay, well the post baking process actually uh, that's making the photoresist pattern photoresist to be stable and form, right? So if you wanna like remove the easily remove the photoresist after certain patterning, for example, metal lithophore patterning, basically in this process, you put the photoresist and then you kind of deposit, evaporate the metal, molten metal, and then to deposit the very thin layer of metal, and then you're going to remove the pattern, the PR, to leave only the metal pattern on the substrate. So in that process, basically your photoresist, even though the photoresist is the protecting layer, in this step, in this particular step of lift off, the patterned PR should be easily to be removed. So in this case, the post baking is not really recommended. Okay, it's just a short, just a quick or short uh, photo or post baking or just soft baking will be okay. All right. So just again for the metal lift off patterning, just avoid any foam post baking process. Okay. All right. Okay. PR remover. So after the process is over, and then you want to remove the photoresist, right? And then it's residues. So usually we use the organic solvent like acetone. That's usually sufficient. This is usually sufficient for the most of the positive photoresist. Sometimes it may be not enough. You can see that, right? Actually, when you work on the clean room, after this removal, just simple acetone removal is done, but still you see some residue on the substrate. And then some commercially available stripper is available to apply. Also, uh, you can use plasma etching with the O2. This is process we call etching. Is sometimes effective for removing organic polymer debris. Um, so, but usually we don't do that. Sometimes you want to do piranha cleaning after the PR removal because uh, basically you want to kind of either you recycle the vapor or you want to move another mask patterning step. So you want to make a like a, you want to see you want to keep the pattern on the vapor, but you want to remove any unwanted material. So piranha cleaning is necessary to completely remove any PR and its residue. Okay, resolution in photolithography. Um, so where the minimum picture size is a measure of resolution of this process. So when I work at cleanroom in school level, right? We are using some UV wavelengths, and then it's very hard to get down to 1 micron, or sometimes 2 micron patterns. 2 micron is kind of a minimum at the time because the resolution in this UV photolithography is like kind of limited in that pattern size. So those resolution is limited by a couple of factors, like there is a light diffraction through the mask, right? And then there is a there is also uh, misalignment is also cause some problem resolution between the if there is already some pattern located on the vapor, and then you want to align the mask pattern with them, right? Then small misalignment also eventually cause the errors, and then that also cause the resolution is down, right? So that's important factor. Um, and then the vapor flatness, right? It's a uniform vapor flatness is necessary to have a good overall resolution through the photolithography. So there is some simple equation is available to kind of to get certain resolution based on the wavelengths of the UV light. So over here, this is a mask. You see the mask, and this is a substrate with the photoresist on top, and then there is a blank pattern here B, and the cover the pattern here B, and then the another blank pattern here B size of B, and then if you apply the UV light on the back side of the mask, then you may expect like a very clear like a rectangular exposure of the light and then pattern on it. But in reality, actually, this is something that in reality, this is something that you should expect. Actual transfer, actually, you have a high intensity applied on the middle of the each blank pattern, and then through the edges it goes down and quickly. Like this is like a delta function. Like this is like a delta function because you see if you're familiar with the optics, right? You have uh, um, like a the periodic pattern, like you have blank and then the cover and blank and cover, and then you send this signal like you send the incident like through the hole. Then in the optical pattern, actually after this is like a, uh, sync function, right? So that's why the like light intensity is like it's work like a sync function like that. So uh, basically, after developing, right, your middle, whatever the in the middle is like developed because it exposed more. So that's the photoresist maybe decomposed more. So they resolve easier than the other pattern around the side of the this big bump. So during the developing, even though you expect the all the opening area developed at the same time with the same rate, but not really. In the middle is developed faster, and then during the edge of the pattern is getting slower because there is more dose of the UV light in the middle. Okay, so basically, there is S and then G is the PR thickness, and S is the um, what is this? Okay, the space between the mask and the PR. So those equations give you some idea what is the resolution, but at school, probably 2 micron is kind of a minimum feature that you can achieve. Okay. Okay. Well, this is very important table actually. It's very practical table. When you when you develop the process, when you develop when you try to find out the best optimal dose of the UV light and also developing time for the certain um, developer. Basically, you have a kind of trial error steps unavoidable because you really don't know what's going to happen. Um, so so that's what ideally you want to see this is vertical like a clean pattern on the vapor like right, but sometimes you have like an undercut like this, right, for the positive photoresist. You also have an undercut for the negative photoresist, or you have overcut on the positive photoresist. So you have a certain variation in somewhere here. Sometimes if you have overdose or overdeveloping, then actually all the patterns actually is gone. Um, so to figure it out, to get down to the really good pattern, and then you have kind of trial error based on this. So for example, if you are using positive photoresist, and then if you take a look in closely, where basically after developing, you put this vapor with the patterned PR under the optical microscope, and then you can find out when you focus on top of the photoresist, you see the size of the um, hole or width here, and then if you focus on the vapor, and then you see the size of a hole is bigger than on top of the photoresist, that means there is undercut, right? So after kind of observe those patterning, and then if there is undercut for the photoresist developer, after after photoresist developing, well, you can conclude that either dose of the UV light is high, right? High means it could be intensity is too high, right? But normally you have no control of intensity. You have a control of time of exposure. So that means the basically you too much exposed for for a long time, right? So you should kind of reduce your exposed time if you see the undercut, okay? And then the influence of a developing time is less for the undercut. So you need kind of, if you see this pattern undercut, then you should play with those time through the UV light. Okay, if you see the like overcut, that means your dose is lower than the normal. Okay, so you should increase the exposure time for the UV. Okay, or in this case also your developing time may be too long, so you should like shorten your developing time. So you can kind of play with those tables and then to find out best combination of those time and then developing time to get this vertical shape of the photoresist. Right? I'm just going to skip the negative photoresist, but usually dominantly affected by the dose, not from the developer. Okay. Okay. Well, now we move on to the wet bulk micromachining. So bulk micromachining is basically wet means you pattern, you make certain pattern, right, through the, right, with some chemicals, right, some wet chemicals. Okay, and then bulk means that actually you etch out, you remove like lots of material. Okay, as shown in this figure, right? This is the like a backside. This is usually see the pattern from the like a backside of etching. Um, so right. So because well initially the rectangles over here, initial rectangle. This is like a one side of the wafer, and this is the other end of the wafer. So it started with a big rectangle, but at the end is the other side of the wafer. You have a small rectangle, right? So it's kind of like a pyramid, right? The size of the rectangle is kind of reduced down to the other side of the wafer. Okay. Why that happened? Why they kind of etch it with some kind of angle, right? Because the silicon this is like a crystal structure, and then they have a certain crystal directionality that the making certain direction of etching is easier than the other side. Okay, so certain direction of the cutting is using the wet chemical is easier than the other like a lateral etching. So that then make a certain unique angular etching pattern on the substrate. Okay, so this is like a unique like a silicon atomic structure and the property cause this interesting pattern. And then it's a kind of a basic etchings using like some patterns. Also, this is a well, basically the topic over here is a well, I'm sorry, this is like a small topic. So we talk about to talk about wet bulk micromachining. Basically, we start talking about silicon atomic structure, and then we cover about the etching, basic of etchings, and then we talk about the silicon and glass of their isotropic etching. Isotropic means it's not direction dependent, right? It's etching everywhere at the same rate. That's isotropic. And isotropic means there is some directionality of etching of silicon. So we'll talk about this. So what is this? This is, what is this? This is the, well, etching speed is different. So this is called anisotropic etching, right? And then there is etch stop method also. You have you need a certain way to stop the etching, right? Otherwise, it is very hard to control the pattern. Okay, so this is like a small topic under the wet bulk micromachining that we'll talk about right now. Okay, well, so let's start to talk about crystal structure. Okay, this is like when you learn about some structure of metals and other component. This is like the basic stuff that to understand the crystal structure, right? So this is simple cubic structure like here, and then this is the uh, this is face-centered cube. This is the a body-centered cube, right? Body-centered cube, and these are three representative like structures. Silicon is not one of them. So basically, we'll talk about the crystal structure or amorphous materials. Okay, like a silicon is crystal structure, right? And then the glass is not crystal, so it's amorphous structure. And then it could be single crystalline or polycrystalline materials like polysilicon versus single silicon. Okay, so we'll talk about this a little bit. Also, the periodic arrangement atom in crystal is called it is called lattice, right? So so this is like an example of lattice. So like a simple cube, if you take a look into the structure from the like a top, right? This is the shape, and they kind of contact each other at the edge of the circle, all right? So like that. This is called a simple cube. It's a layer in nature. Um, so everything is the same atom, like A, and then the body-centered cube. You have one atom in the like in cube in the middle of the volume. There is one atom here, and then at each corner there is a like a 1/8 of uh, atom is there. So on the from the top view, this is kind of a shape. Um, this is red one is in the middle of the cube, and then around there is a additional atom here. So, but they are not touched like this SC. Like there are little space to have certain distance with the center body center the atom. So there needs some space. So that's kind of the shape from the top view. Face center the cube means that at each face there is a like a half of the atom, and then at each corner, so 1/8 of atom is located at. So that's kind of called. That's why it's called the face centered cube. And then from the top view, it's a little complex, but it is like a B, C is like a little, in the, from the, it's hard to explain, but that's kind of a shape from the top that you're going to see it. And luckily we have a good website and out there, so you can kind of search it, and then you can take a look into how they look like, right? Okay, so this is like a single crystalline, and then polycrystalline and amorphous is they like a different shape. This is like a this one single crystal structure lattice is kind of keep going on, so no, it's just overall is all everything is periodic. Amorphous, no periodicity of the between the atoms, right? Polycrystalline is periodic with one section, but they kind of and then the other section, but they kind of many crystalline actually meet in within the certain area, right? So this is called the polycrystalline. So I strongly recommend you to visit this website. This is the website built under the I think Birmingham University in Utah. So there are some websites that explain. Let me correct it. Explain the crystal structure. Okay. So let's see. All right. So over here, um, so this is crystal plane and semiconductor. So we'll talk about this Miller indices soon, but to talk about the directionality, actually, we are going to use Miller indices. For example, like you can think about this is like a x, y, g coordinate, and then in this vector, right? In this vector, we can say that this is like a only x direction is only available, no y and g. So this is called like a 1 0 0 1 is like a to make a unit vector. You can make this 1, 0, 0 means there is only one component in like x direction, right? And then or in the other say this in g direction if 1, 0, 0, 1, and then the y direction is 0, 1, 0, right? On the other hand, you can define the another vector like this, right? There is no y component, there is only x component and then the g component. So that this vector could be 1, 0, 1, right? So it's same as here, no g component, so 1, 1, 0. So you can say that. Also, in three-dimensionally, right, you can find out the 1, 1, 1. That's pass through this origin to the like a 1, 1, 1 coordinate. In this direction, this is 1, 1, 1. And then the other direction, you can, depending on the directionality, you can, put some negative sign on it. So that's kind of a Miller's indices that we're going to use it. If you go down here, okay, there is a simple cube and body-centered cube here, right? So they looks like here. So please visit. You need some Java application to see some simulation, but uh, this is a good website to take a look into. So for the silicon wafer, right? Because they are built up with different directionality. So when you buy the silicon wafer, and then to differentiate their crystal direction, they kind of cut the edges in different shape. If you see the 100 n-type, then you have like a cut at the left and then the primary cut to the right, and in this code. So you have two cut. If you have a 100 p-type, then you have like a one cut here and then in 90 degree, and you have second cut. Okay, so there's a, and then if you have certain other directionality, 111 direction p-type or 111 direction of n-type, like a p-type, you have only one cut, and n-type with 111 direction, you have a two cut, but it's like a 45 degree, not the 90 or 180. So with this cutting, actually you can differentiate the wafer, right? Otherwise, the after put out the like a tag, when you buy the vendor, they come with the like a post that this is the wafer 100 n-type. But when you actually working with the just bare wafer, you don't have any those tag anymore. So you see this cut of the flat surface, and then you need to figure out what kind of wafer you are dealing with. So please visit this website, then you can see more information over here. Okay. All right. This is a atomic packing factor, means the how, well, on this cube, right? How much volume was occupied by the atom? That's the atomic packing factor. So, well, please search the how to calculate this atomic factor. But I'm not going over in detail. But what I like to say that FCC, they have a highest like occupying atom packing factor here, like 0.7405. Okay, body centered one is 0.6802. Okay, so let me stop it here and then we'll keep going on.